Hello, my name is Mad Max. In the last couple of episodes, we heard a really interesting story. The story of the Big Bang. We learned how the theory of the Big Bang was first formed. We learned how it was proven. We learned where the first elements ever, right, element 1 to 4, were born during minutes 2 to 30 during the Big Bang. And we learned how stars were formed and how the first stars had fusion going on inside the stars, and how this fusion, right, bigger and bigger particles forming, create all the elements up to iron, and to everything heavier than iron is formed in a supernova. That's what we learned so far. Now, we just had a supernova explosion, and this gas cloud, the leftover from the supernova, that is the beginning of our solar system. How do we know that? Well, we learned in the last episode that everything heavier than iron, right, or not just iron, but let's say everything heavier than nickel, okay, can all of those elements, like uranium, like gold, like silver, like platinum, like polonium, and whatever, can only be formed during supernova explosions. They can only be formed during supernovae. We have those elements in our solar system, right? We have uranium, we have gold, we have silver. So that right there is proof that our solar system was born, it came into existence with material from a supernova explosion. Okay? Very simple proof. Alright, so we just had the supernova explosion, and now we have a cloud of gas 620 trillion kilometers in diameter. What's 620 trillion kilometers? I have this really thin pen right here, okay? I make a dot, okay? This dot is about 1 millimeter in diameter. Can you even see? Yeah, this dot, okay? Let's say this dot is the Earth. Alright? And let's say the Earth is on one end of this cloud. Then the other end of the cloud, if the Earth would be this size, the other end of the cloud would be 5 kilometers away. That is how big 620 trillion kilometers are. We had this ginormous disk of all the elements you can imagine just sitting there in space. Now, this happened about 5 billion years ago. But the situation is not that different from the situation about 1 billion years after the Big Bang, when the first stars were formed. After the Big Bang, when the first stars formed, we had a situation similar to this. A big cloud of gas. And what happened? Stars formed. The only difference now is that suddenly we do not only have hydrogen, helium, lithium, and beryllium, we have all of the elements. That's the difference, okay? That's a big difference. We suddenly have all of the elements. So it's a little bit different from the first stars that formed about 1 billion years after the Big Bang. So, in this cloud of gas, we had particles flying in all different directions, okay? It was an absolute chaotic mass of protons, of neutrons, of nuclei, of whole atoms, just flying in random directions, okay? So let's say each single one of those arrows is just one particle, and the length of the arrow is the speed of the particle, and obviously the direction of the arrow is the direction of the particles flying in. So we have chaos. We have just all different kinds of particles going in different directions. Let me actually use black for that so you can see it better. So again, the situation wasn't that different from when the first stars formed, right? So remember what happened back then? Well, we had gravity, right? Every particle has gravity, and gravity is pulling everything towards the center of mass. Okay? Towards the center of mass. And just by that, just by a set of simple rules, which we call the laws of nature, out of chaos we can get order. How? We have chaos, right? But we have a center of mass. Let me add some more particles right here. Okay. So each area is a particle. This big X in the middle is the center of mass, okay? Everything is pulled towards the center of mass. Now, you can understand that a particle like this, right, that has a slow speed and is moving to the center of mass to begin with, will be trapped here, right? Whereas a particle like this, which has a pretty high speed and is going away, can escape. Or a particle like this, which has a pretty high speed and is going in this direction right here, will not be pulled into the center. Because it's flying so fast, right, it will start to rotate around the center, just like the Earth rotates around the Sun. It's so fast that the centrifugal force, right, the centrifugal force acting outwards because of the speed of the particle is exactly the same as the gravitational force pulling it inward, okay? This is the center of mass, this is our particle, it's going really fast, and because it's going fast, centrifugal force outwards, gravity inwards, it starts to rotate. So this gas cloud we have, over time, will start to rotate too. Because all the particles that are either too fast, so they can escape, or that are too slow, so that they are being pulled into the center, right? All those particles are basically gone. They're either escape or they are trapped into the center. So the only particles that are remaining are the particles that have had the right direction and the right speed, so that they could start to rotate. All the other ones are just gone, basically filtered out. And obviously, you don't have one direction of rotation yet. Obviously, you will have particles rotating in a different direction, right? Like this green one. You have this black particle rotating like this, and you have this green particle rotating like this. However, over time, those particles hit. They hit each other, right? So, by hitting each other, speed goes down, direction changes, so a couple of them escape, a couple of them fall to the center of the gas cloud. But over time, the important thing, over time it will average out, and over time you will only have one direction of rotation remaining. Because all the other particles got filtered out over time. So again, at first we had chaos, absolute chaos. But then just by waiting a little bit, and just by the laws of nature, just by gravity, suddenly it's getting more and more ordered. Now we have this cloud of gas that is being held together by gravity, and that rotates, okay? And it kind of spirals inward. So what happens is that the cloud of gas, our 620 trillion kilometer cloud of gas, gets smaller and smaller and smaller and smaller. Our solar system today is only 8 billion kilometers in diameter. What happens when our cloud rotation, our cloud of gas that rotates is getting smaller? It starts to rotate faster. Just like an ice dancer, when an ice dancer rotates and the ice dancer pulls the arms close to the body, it starts to rotate faster. Because when you have more mass closer to the rotational axis, the speed has to increase. Another simple law of nature. So the speed of rotation increases. And what happens when you have a sphere that rotates really fast? Well, it doesn't stay a sphere, like the Earth. The Earth is not a sphere. Because the Earth rotates, right? Because the Earth rotates around a rotational axis, okay, it's actually an ellipsoid, right? It's not a perfect sphere. because those parts right here are farther away from the rotational axis, but they have the same rotational speed. So they have higher speed. That means they have a higher centrifugal force, and this causes the Earth to get an ellipsoid, and this causes our protostellar disk, or this causes our nebula to become a disk. Okay, it's no longer a nebula, it's a disk. You have a lot of mass in the center, right? A lot of mass in the center, and then you have a disk. Okay, it's a horrible picture, let me do this again. It looks a little bit like, you know, our galaxy in small. Our galaxy 2 has a lot of mass in the center, right? And then has those arms that are in a plane. Okay, this is a horrible picture, right? So you have a lot of mass in the center, and then you have this disk. And here is an actual picture of this so-called protostellar disk. This is an actual picture taken. Pretty cool, huh? Alright. So, over time, the mass and the density of the center of our protostellar disk, right? It's no longer a cloud of chaos, it's now a pretty ordered system. It's a rotating disk with a lot of mass at the center. Over time, the density gets so high in the center and the temperature gets so high in the center that suddenly fusion starts again. Suddenly we get a new star again. Just like the first stars that were born about 1 billion years after the Big Bang. Basically the same thing happens again. Right? The same thing happens again. But this time we have a lot more different elements. This star that is being formed is our sun. That sun right there. If you would go outside, you could see it. It is our sun. So, but we are not living in a stellar disk, right? We are not living in a stellar disk. We are living on planets. So, how did the planets form? Well, the material in the disk, right? The material in this disk-shaped nebula, okay, cools down over time. It cools down over time, okay? It irradiates electromagnetic radiation, and by that it's giving energy away, and it's cooling down. It's cooling down over time. Now, if you have water vapor, okay, if you heat water, it becomes vapor. But when it starts to condense, it gets liquid again. Now, the same thing can happen. Same thing can happen with all those elements, okay? When they are at a certain temperature, they are a gas. But when they cool down, they start to condense. And they all condense at different temperatures. So, while this cloud of gas, this disk, is cooling down, some elements start to condense. One after the other, they start to condense. So it's no longer a gas, you have parts of dust in your gas. Just like dust in your room, right? If you don't do anything about it, at first it's really small, but over time it gets bigger and bigger and bigger until you have those massive dust particles on your floor, right? The same happened and happens right now in other parts of the universe, in this disk, okay? Some elements condensate, and then they start to collide with each other, and they get bigger and bigger and bigger and bigger. So at first you have specks of dust, right? And then later you get a little bit bigger specks of dust, and then later you get stuff the size of asteroids. Asteroids collide, and you get bigger and bigger and bigger and bigger bodies over time. Okay, we see, if you look at our moon, we see all those craters. Where do those craters come from? Well, asteroids pounding the moon, but the mass of those asteroids hitting the moon is not gone, right? Part of it escapes. A part of it escapes, but most of it stays on the moon. So that means whenever an asteroid hits the moon gains mass. Whenever an asteroid hits the Earth gains mass. So over time, those asteroids hit each other, and they get bigger and bigger and bigger and bigger. Now, while this is happening, all the time, the sun had fusion going on. And because you had fusion in the sun, you get a phenomenon called stellar wind. Okay? Sun wind. Here's a picture. Now, it sounds complicated. It looks complicated. It can be really complicated when you look at it in detail. But solar wind is nothing else than just electrons and protons basically being ejected from the sun. Now, an electron and a proton and, photons, electrons and photons mostly, they don't have a lot of mass. They don't have a whole lot of force, okay? Because they're really small. They're really fast, but they're really small. It's like the difference of a car hitting you with 10 miles an hour or a feather hitting you with 10 miles an hour. So feather with 10 miles an hour does not hurt that much. It does not transfer that much kinetic energy in your body because the mass is so low. But it has some kinetic energy. And if you have a single atom, right, and it's just being hit by photons from one direction and electrons from one direction over and over and over, it will propel this atom outwards. It's not a lot of energy, right? It's not a lot of energy. But over time, it's enough to be able to change the path of all those small little atoms. So, let's make a picture. I need actually a new piece of paper for that. I already killed 2 trees. Okay. Okay. Alright. I don't really know what I'm doing right now, but let's see how it turns out. It's horrible. God. Okay. Alright. So, here's how it looked. In the middle, it's a complicated picture, but one thing after the other. In the middle, you have this newborn star, the young sun. The blue arrows are sun wind. Then you have massive objects, asteroids and stuff, that already formed, that rotate around the star, rotate around our sun. And then you have this wiggly line, right? And that is a cloud of gas. That are all of the atoms that didn't condensate yet. It's still too hot for them to condensate. And they are light enough that they can be carried outwards by the solar wind. The asteroids are way too heavy to be affected that much. They are affected, but not that much, by the solar wind, right? By the solar wind. So only those elements that are still gas are really affected by the solar wind, not the asteroids. So what does this mean? That means that just by sun wind and just by the fact that different elements condensate at different temperatures, this system, right, this disk, starts to order itself. In the beginning, it was absolute chaos, just particles flying in different directions. But then over time, by simple laws of nature, by gravity and by solar wind, just by those two, suddenly we get order. Suddenly we have some elements forming bigger and bigger bodies rotating around the sun, right? And we have gas getting farther and farther away from the sun. It starts to order itself. And in fact, if you look at our solar system, what would you see? If you look at our solar system, in the middle we have, obviously, our sun, then we have Mercury, then we have Venus, then we have Earth, then we have Mars, then we have an asteroid belt, and then we have I don't know the order, I'm sorry. And then we have Uranus, we have Saturn, we have Neptune and Jupiter. Okay. Like this is the sun. And then we have also planets. Now, do you notice something? Do you? All those planets close to the sun are rock planets. All the planets farther away from the sun are gas planets. Why? Because of the sun wind. Why? Because the elements those planets, those gas planets are made out of, condensate so late that they could be transported far away from the sun by the solar wind. Whereas the elements those planets right here and the asteroids are made out of condensate so soon that they weren't affected by the solar wind as much. Right? For example, silicium isn't affected by the solar winds that much because it condensates so fast. So we now have planets, we have rock planets that consist largely out of silicon, right, and iron and stuff like that. All elements that condensate at a pretty high temperature, so pretty soon. And then we have gas planets far away that consist largely of hydrogen and helium, that stuff that condensates at really low temperatures, so really, really late. So just by gravity and just by the fact that those elements condensate at different temperatures, we have a highly ordered solar system. That is the reason why we have rock planets close to the sun and gas planets far away from the sun. Isn't that absolutely amazing? I found this to be one of the most astonishing facts I've ever heard. That you can start with a cloud of random particles going into random directions, right? Totally random. And then just over time, just by the influence of gravity and just by the influence of thermodynamics, of stuff cooling down and stuff condensating at different temperatures, just by those really simple things happening, we get this. From chaos, we get order. You're wondering, how the hell do we know this is what happened? Well, we know the composition of the sun. We know the composition of other planets. We didn't land on Venus and got rocks from Venus, but we got asteroids that hit Venus and bounced off. We got asteroids that hit Mars and bounced off. We know the composition of Mars, we know the composition of Venus, we know the composition of Jupiter and the Sun, we know the composition of our Earth, and we see a trend. We see that if we look at distance from the Sun, right? If you look at distance from the Sun, if you look at distance from the Sun, that's distance from the Sun, and that's concentration, right? Those elements that condensate soon get less and less the farther we get away from the sun. And those elements that condensate really late, right, at low temperatures, like helium and hydrogen, are getting more and more the farther we get away from the sun. We have those trends. And what I just explained to you is the best explanation for those trends. It's the best explanation we have that does fit with all of our observations, so it's the most likely one. But this just leads to more questions, doesn't it? This leads to the question, okay, now we have our young solar system, but how exactly did the Earth evolve? How exactly did the Earth evolve to what we have today, to what we are living on today? How did we get our moon? Those are questions that I will answer in the next episode. My name has been Mad Max. Thanks for watching.